Swayam Prabha. Digital India. Educated India.
In the previous lecture, we have seen how to solve problems by using free body diagrams, isolating subsystems and considering forces on each subsystem. Also, how the subsystems affect the motion of one another was taken into account by looking at the constraints and equations for constraints. Two examples that we took were, one, the Atwood's machine, where I had two masses going around a pulley, M1 and M2. The other example that we took was a mass sliding down a wedge like this, and the wedge could also move horizontally. In these examples, we ignored a ubiquitous force that is encountered every day in our lives, and that is the frictional force. This lecture is going to be about how do we take into account the frictional forces and how does it affect the motion of a particle. There are, when the body moves, we see that its motion is usually resisted by the surface on which it is moving. So if I apply a force F this way, there is, the surface applies a force called frictional force that opposes this motion. Even if the body is not moving, frictional force has a tendency to oppose the tendency to move. Another example of frictional force is the drag force or the viscous force that we encounter when a body moves through a fluid. This force also opposes the motion. In this lecture, we will be looking at both kinds of forces. So let us start with a force of this kind, which is when a solid moves on another solid. Let us take a mass M1 and another mass M2, and let me pull this mass with some force F. If you recall your everyday experience, you would see that the top mass or the bottom mass doesn't move until the force has reached certain value, and that is because their tendency to move is being opposed by the frictional force either between these two masses or between this mass and the surface on which this mass is resting. So first question is the frictional force of constant amount, or does it vary as I vary this force? Let us give an argument. If suppose the frictional force were of constant amount, and that means this mass M1, which is on the top, experienced a constant force in this direction, then even if I did not apply any of this force F, because of this force the mass would tend to move this way, and I know that doesn't happen, and that means the frictional force adjusts itself as I apply the force. How does it adjust itself? It is just sufficient to oppose the motion or the tendency to move. So for example, if I take a mass sitting on a surface and I try to pull it by a force F, its tendency to move would be opposed by this frictional force. It is observed experimentally that the maximum frictional force that a surface can apply on a given mass is given by mu, where mu is a constant, times n, and I'll put a subscript s here to indicate that this is static friction. Friction is slightly different when the body starts moving, and we'll be discussing that. Notice that I have written a maximum here, and that is to indicate that that is the maximum possible frictional force that is available. Of course, the frictional force adjusts itself as I vary this force. So the maximum possible is this, otherwise it is always less than, just sufficient so that this body doesn't move. What is N? N is the normal reaction of the surface on the body. So N is the force that is perpendicular to the surface on which the body is moving. So the maximum frictional force on a block on a surface is given by F max, which is mu s times n. If I apply a force here, the frictional force adjusts itself so that the body doesn't move. If I plot the frictional force against the applied force F, which is given here, you would see that frictional force goes exactly as F, this angle being 45 degrees, so that the slope of this line is equal to 1. And right when the applied force exceeds the maximum possible frictional force, the body would start to move and the frictional force may become a constant. I am drawing this line because this force drops slightly, as I will explain in the coming few minutes. Of course, once the body starts moving, the frictional force is slightly less. So that I write as friction kinetic, and it is given by mu k, the normal reaction. So that if I again plot the applied force versus friction, it will go up at 45 degrees until the maximum value of the frictional force mu s n has been reached, where n, as I said earlier, is the normal reaction of the surface. And as the body starts to move, the force drops a bit, but then is a constant. This is equal to mu k n. This point obviously is mu s n. Let me redraw it for clarity. So as I take a body, apply a force, the frictional force increases in proportion to the applied force. This, as I said earlier, is 45 degrees, and then when it reaches the maximum mu s n, the body will start moving and the friction force drops slightly, this value being mu k n. To give you a feel for what mu s and mu k are, let me give their values in the next slide. For some materials, the value varies from material to material. So this is, we will take steel on steel dry surface, we will take steel on steel greasy surface, and we will also take metal on ice and tires on road. Mu static for steel on steel is about 0.6 when they are both dry. Steel on greasy is 0.1. You can see why we grease steel. It reduces the friction value quite a lot. Metal on ice, static is not known because it slips past quite a lot, and tire on road is 0.9. You can see we really need a lot of friction for tires on the road so that they don't slip. The moment body starts moving, steel on steel drops down to 0.5, steel on steel greasy drops down to 0.05, metal on ice is about 0.03, almost frictionless, tires on the road comes down to 0.8. I must give you the source of this. This is Merriam and Craig Dynamics. That's where I've taken these values from. So what we have seen is, as the body moves on the surface, it can feel either the static friction, and once it starts moving, then there is kinetic friction. Kinetic friction is slightly less than the static friction. Let me now see how I can estimate the coefficient of static friction between two bodies. This can be easily done if I consider the motion of a block on a ramp or an inclined plane of angle theta. Since without friction the body has a tendency to move this way, there will be a frictional force trying to stop it this way. If I make a free body diagram of this block, it has its own weight mg pulling it down, a normal reaction n due to the surface, and a frictional force this way. Let us consider the body in equilibrium and see what happens. Value of the coefficient of static friction can be easily estimated if we consider the motion of a block on an inclined plane of angle theta, and here is the free body diagram as I previously made. There is weight mg, normal reaction n, and the frictional force this way. This angle is also theta. If the body is not moving, then I should have all the forces balancing each other, and therefore n equals mg cosine of theta, and the frictional force, let me write it as F, is equal to mg sine of theta. These are my two equations. Let us see what happens when I start increasing theta. This body has weight mg, n, friction F, and mg, this component of mg is pulling it down, which is mg sine theta. As I increase theta, mg sine theta goes up, so the body is being pulled down by larger and larger force. When it surpasses the maximum possible frictional force, it will start sliding down. Let us see what is maximum possible frictional force. Friction maximum, as I told you earlier, is equal to mu s times n, and as we saw in the earlier, n is nothing but mg cosine of theta, because there is no motion perpendicular to the inclined plane, and therefore F maximum, or the maximum value of friction, is mu mg cosine of theta, and this implies that when mu mg cosine of theta, that is the frictional force, becomes less than or equal to mg sine of theta, the body would start sliding down. Let me cancel m, let me cancel g, and therefore when mu s is less than tangent of theta, the body will start sliding down. So you take an plane, keep tilting it until the body just starts sliding down, and that angle you take the tangent of would give you an estimate of the static coefficient of friction. That is a practical way of quickly estimating what the coefficient of static friction is. So we have seen that frictional force is given by mu, depending on whether it is static or kinetic, mu s or mu k, times the normal reaction of the surface on a body. Let me now take you back to Atwood's machine that we discussed in the previous lecture, a slight variation of that, and see how frictional force changes the tensions here. Recall, when I solved this problem in the previous lecture, then I had assumed that all the surfaces are frictionless. Now let me take the same problem where mass m1 and m2 are at two ends of a rope, and it is passing over a pulley, and pulley is fixed, pulley cannot move. So it's a, let me just write, fixed pulley. Only the rope slides over the pulley, and there is friction between the pulley and the rope. Earlier when we solved this problem, we assumed that the tensions here were equal. Now due to the frictional force, the tensions are going to be different. Let me call this T2, let me call this T1. Let the mass m2 be greater than m1, so that the rope has a tendency to move this way. Let us see how friction affects things here. I am pretty much repeating what I have done in a previous lecture on static friction. I do it here for completeness. Since the rope has a tendency to move in this direction, the frictional force on the rope is going to act this way. This is the frictional force. This is mass m2, as I said earlier, and this is mass m1. If I want to see how friction changes, let me for that consider a small piece of rope. This is somewhere here that I am making slightly bigger here, and consider its free body diagram. If I join from the center of this to the center of this pulley, there is normal reaction on this small piece of rope. Let me call it delta n. Since the tension on this side T2 is going to be greater than T1 because m2 is greater than m1, the tension increases this way. Let this tension be T plus delta T. Let the tension on this side be T. Let this small piece of rope make an angle delta theta at the center of the fixed pulley. So let's make a neater picture of this part only. So here is this piece of rope. It makes an angle delta theta at the center. The tension in this way is T plus delta T. Tension this way is T. This is the normal reaction, and the rope is in equilibrium. Am I missing any force? Of course I am missing a force, because the rope is not moving. There is friction that balances things, balances T, the imbalance between T and T plus delta T, so that the rope doesn't move. Let us now balance forces. The components of the tension in this direction balance N. If I take the components parallel to this line and perpendicular to this line, this is the direction for N, this is direction perpendicular to it. The components of T in this direction balance N, and therefore I am going to have T plus delta T. This angle, as you can see, is going to be delta theta over 2, and this is a very small angle, so sine delta theta over 2 can be estimated by delta theta over 2 itself, plus T sine delta theta over 2 is going to be equal to delta n. This angle again is delta theta over 2. And the second equation, T plus delta T cosine of delta theta over 2 minus T cosine of delta theta over 2 is going to be equal to the frictional force F. Let us then write these equations again. I have T plus delta T sine delta theta over 2 plus T sine delta theta over 2 equals delta n, which can be approximated for a small delta theta as 2T delta theta over 2. I replace this whole thing by delta theta by 2 plus delta T delta theta over 2 equals delta n. This is second order term, so that can be taken to be 0 in the limit that I take delta theta going to 0. So I have this cancels, T delta theta equals n, or which I had earlier written as delta n because this is a very small normal reaction. And the other equation, which was T plus delta T cosine of delta theta over 2 minus T cosine of delta theta over 2 equals F, can in the limit of delta theta going to 0 be written as delta T equals F. These are my two working equations that will determine for me how the tensions are related when friction is present. Let us now take the extreme case of when mass m2 just balances mass m1. This is the friction, so that in that case friction is going to be maximum, and that is going to be equal to mu delta n on that small piece. So I have equations from earlier, T delta theta equals delta n and delta T equals F max, which is mu delta n, which in turn from this equation is equal to mu T delta theta. So I have a relationship between the tension, change in it with respect to change in theta. That gives me delta T equals mu T delta theta, or delta T over delta theta equals mu T. Limit delta theta going to 0, it gives me dt over d theta equals mu T. This equation is quite easy to solve, and you have been doing it in many different places. The solution for this comes out to be T equals some T 0 e raised to mu theta, where this T is being measured as a function of theta. T0 is at theta equals 0. So let me just again make a picture and show you that this was mass m1, this was mass m2, T1, T2, theta is increasing this way, T is increasing this way, and if I take this to be theta equals 0, as theta increases, tension also increases. So that you can see in this case T2 is going to be equal to T1 e raised to mu times pi. Since the tensions balance the masses, I also have m2 equals m1 e raised to mu pi. G cancels from both the sides. You can see because of the friction mu, a very small mass m1 can balance a mass much larger than itself, which is m1 times e raised to mu pi. This has practical uses. In fact, unconsciously, if you recall, you have been using it. Suppose you tie a rope or a clothesline in your backyard. You generally put it on the nail and wrap it around a few times. You are unconsciously using the fact that tension as angle goes up goes as T0 e raised to mu theta. So that with a very small force on one side you can balance a large force on the other side. Another practical use is the capstans and the dockyards where a huge ship is stopped from moving by taking a rope and wrapping it around these capstans. If you wrap it around many times, theta goes up, so that with very small tension on one side, a huge tension builds up on the other side, and that can stop the ship from moving. You can also do an experiment to check the validity of this expression at home. How do I do that? You take a pen and put a small object, maybe a pin or a key on one side, and a large object on the other side of a string, and try to balance it. As we said earlier, suppose this mass is heavier, m2 would be in this case be equal to m1 e raised to mu pi. So I'll take this pen, wrap a string around it once, and this relationship would be satisfied. Let me give it one more wrap. If I do that, then I should be able to have m2, let me call it m2 nu, equals m1. Now it has gone around one more time, so I add another 2 pi to theta, e raised to 3 mu pi. Let it go around one more time. m2 nu prime is going to be m1 e raised to 5 mu pi. By seeing how much mass can you balance with a given mass as you wrap the string around, you should be able to confirm the validity of this formula that we just derived. You should see that m2 nu prime divided by m2 nu is equal to e raised to 2 mu pi, and that is also equal to m2 nu over m2. This ratio would remain the same as you keep wrapping the string around more and more and more. Let us now solve a few problems involving friction. 3 of these problems are taken from the textbook of Merriam Dynamics. The first problem is, if I have a truck moving at a certain speed, and suppose there is a box here. The truck suddenly brakes. You know from experience, if the truck brakes, the crate or the box is going to move this way. If I am given the coefficient of friction here, that is going to resist this motion of the box. So frictional force is going to oppose this movement. What I want to know is, suppose initially the truck is moving at a speed of 72 kilometers per hour and it brakes, and suppose mu is given to be 0.3 between the box and the bed of the truck. what is the minimum distance S over which the truck should stop if it uniformly decelerates so that the box doesn't move. To repeat, I am braking and I want the truck to stop. I want to find the minimum distance S so that the box doesn't move. Obviously, when the truck slows down, I need the box also to slow down. It should not happen that truck slows down faster than the box can slow down. If that happens, box will start sliding. So, the maximum deceleration on the box that I can have is F max, the maximum friction, divided by the mass of the box is maximum deceleration or negative acceleration. And it is this deceleration that is what the truck can also have. If it slows down faster than that, the box will start sliding. The friction will not be able to stop it. So let us see what is the maximum friction. F max is going to be mu mass of the box times g, because for this box which is not moving in vertical direction, n is same as mg. So F max is given by this formula. So maximum deceleration A is going to be mu mg divided by m, which is equal to mu g, which in our case, if I take g to be approximately 10 meters per second square, is going to be 0.3 times 10, which is 3 meters per second square, and that is the maximum deceleration that is allowed for the truck also. And so V final square for the truck, which is 0, is equal to V initial square minus 2 times the acceleration time s. This is going to be 72 kilometers an hour, which if you change to meters per second comes out to be 20 meters per second, and 20 meters per second square is 400 minus 2. I have already calculated A to be 3 times s. That's maximum A. So S minimum that much, and that gives you S equals 200 over 3, which is 67 meters. Of course, if the truck slows down and stops at a distance larger than this, I can do with smaller a. That is no problem. But the maximum A allowed is 3, and therefore S minimum has to be 67 meters. That is one example of solving problems using frictional forces. As a second example, I take a crate or a trolley which can move on its wheel without friction. This is taken to be 100 kilograms. On top of it, I put a box of 20 kilograms and pull it. There is a pulley here, pull it by a force P, the other side of this string is attached to the wall. The coefficient of friction, whether static or dynamic, let's take it to be the same, between these two masses is given to be mu s, almost the same as mu k, is equal to 0.5. And we would like to know what are the accelerations of the two masses in case P is 60 newtons, case 1, and case 2 when P is 40 newtons. Let us see what happens in the two cases. Obviously, when this P is pulling it, since this is a rope going around a pulley, the net force on the upper mass is going to be equal to 2P, that I need not go over again. And since this mass has a tendency to move this way, it will be opposed by a friction F. That is the free body diagram of mass 20 kg. Similarly, the free body diagram for the trolley is going to be, there is nothing here. The only force that by Newton's third law is applied on this is the frictional force in opposite direction F. If I draw it again, showing only the relevant forces for horizontal motion, the free body diagram for the 20 kg mass is 2p this way, friction this way, and for the trolley is friction this way. So, the trolley would move in this direction, accelerate in this direction due to this frictional force. The 20 kilogram mass will also move in this direction because of 2p and the force. Let us see what p I should apply so that they don't slide. That would happen when F is maximum possible. Let us calculate what is F maximum possible, that is mu mg. Mu is given to be 0.5, m is 20 for the upper mass, n mg. On free body diagram I should also show these forces here, mg, n prime, and there is an n here, alright, times 9.8, and that comes out to be 98 newtons. And that comes out to be 98 newtons. And therefore, if 2p happens to be greater than 98 newtons, this fellow would accelerate in this direction, okay. This fellow is moving this way. Maximum force it can have in this direction 98 newtons. This has a force 2p, and this has a force F, maximum 98 newtons. So, the maximum acceleration for 100 kg trolley is equal to 98 newtons over 100 kg, which is 0.98 meters per second square. If the acceleration of the top mass 20 kgs happens to be larger than this, then there will be sliding. If it is less, then there will be no sliding. So, let us see what happens when I apply a force of 2p here, and this is 98 newtons. In case of p is equal to 60 newtons, which was my first case, the acceleration of the upper mass 20 is going to be 120 minus 98 over 20, which is 22 over 20, which is 1.1 meters per second square. And therefore, in this case the two masses, the 20 kg mass and the trolley, are going to have different accelerations. This is going to move with 1.1 meters per second square, and this is going to move with 0.98 meters per second square, and they are going to slip on each other. Let us see the other case when P is equal to 40 newtons, which implies that 2p is going to be 80 newtons. And in this case 2p happens to be less than the maximum force, maximum frictional force. This is 80 newtons, and F max is 98 newtons. So, the friction will adjust itself just to 80 newtons, so that this fellow, this mass, doesn't slip, and therefore you can conclude that in this case this is going to be 80 newtons and there is going to be just sufficient force F so that this does not slip. Is F equal to 80 newtons? The answer is obviously no. You can see it in two ways. First, if I consider the trolley and the mass, 100 kgs together, then on this entire system there is a net force 80 newtons. There is no relative acceleration, they are moving together and therefore their acceleration together is going to be 80 divided by 120, this is newtons, kgs, which is going to be 2/3 meters per second square. But what about the frictional force in between? The question we started with is it 80 newtons? The answer is no, because you see the trolley has only one horizontal force acting on it, that is the frictional force. There is nothing to stop it. So, the moment there is friction, this trolley is anyway going to move. If it moves and there is no slipping between the upper mass and the lower mass, then this mass is also going to move and both move with the same acceleration. Let us look at it from that point of view. In that case, the trolley has an acceleration which is going to be equal to the force, frictional force, which I do not know, over 100. And similarly, the mass, let me write it trolley, so 100 kgs, mass 20 kgs is going to have an acceleration which is going to be 80 with the force with which I am pulling it minus F over 20. And since there is no slipping, because 80 newtons happens to be less than the maximum frictional force, these two accelerations, this and this one, must be equal. And therefore, I should have F over 100 equals 80 minus F over 20. That is 5. So, I have F over 5 plus F 6, F over 5 equal to 80, or F equals 400 over 6 or 200 over 3 newtons, and that gives me the acceleration A 200 over 3 times 100 equals 2/3 meters per second square. So, you see how friction changes the acceleration and how it affects the motion between two bodies that can apply frictional force on each other. As a third example, let me take a chain which is on a rough surface. So, this is a rough surface, and let us take this to be x equal to 0, and beyond this is a smooth surface. This is a rough surface, and I start pulling this chain with a constant force P large enough so that it comes into motion. So, we are not making that any complicated. It starts moving, and I want to know when this chain is fully outside the rough, it has come fully out, what is its speed. Okay. So, let us now make a picture in between when it has come out partially from x equal to 0. The chain is like this, is being pulled by force P. Let this distance be x, let the total length of the chain be L. This then is going to be L minus x. Let the mass of the chain be m, and I want to know when the chain has come out fully from the rough, what is its speed. Let us see what are the forces acting on the chain. There is obviously this force P pulling it this way. There is frictional force, but the frictional force acts only on this part, and so friction, and since it is moving, friction is going to be at its maximum, is going to be mu kinetic m over L minus x, that is the mass of the part in the rough, times g. This whole thing is the normal reaction on the part on the rough. And therefore, if I write the equation of motion, the total mass m of the chain moves with acceleration x double dot. Because if the chain has come out by distance x, its acceleration is going to be x double dot, and this is going to be equal to p minus mu m over L minus x times g. For simplicity, I have dropped the subscript k here. It is understood mu is kinetic frictional force. So, x double dot therefore is given as p minus mu m g plus mu m g over L x. Since I want to know what is the speed when the chain has been fully pulled out, I am not really interested on the variation of x with respect to t. So, I use an old trick which I used in the previous lecture. I write x double dot, which is really d by dt of x dot in terms of x and x dot. So, this I can write using the chain rule as d over dx x dot times d over dt of x, which is nothing but x dot d over dx x dot, which is 1/2 d over dx of x dot square, and therefore, my equation becomes m over 2 d over dx of x dot square is equal to p minus mu m g plus mu m g x over L. Now, I can easily integrate it from x equals 0 to L. So, if I do that and let the speed be v when the chain has been pulled out completely, that is x equals L. So, by integration I get, I am integrating the equation m by 2 d over dx x dot square equals p minus mu m g plus mu m g x over L. By integration I get m over 2 v square equals p L minus mu m g L plus mu m g L over 2, which is nothing but p L minus mu m g L over 2, and that gives me the speed of the chain after it has been pulled out fully. We will see in a later lecture, when we talk about work energy theorem, that this is the gain in kinetic energy, which is equal to the work done by the external force, which is P L when the force moves the chain by distance L, minus the average frictional force, which at the highest is mu m g, at the lowest is 0. So, average is mu m g by 2 times L. This is the loss due to friction. So, energy gain by the work being done minus loss due to friction is equal to the kinetic energy, and this is how I can calculate the kinetic energy. As the last example, let me take a cylinder which is moving around its axis with an angular frequency omega, and let me take a mass here which is free to slide, but because of this rotation is stuck on the wall. The coefficient of friction between the wall of the cylinder and mass m is mu. I want to know what is omega minimum when this mass is stuck on the wall. If I may take a free body diagram of this mass m, it is being pulled down by its own weight and the friction opposes this and there is a normal reaction n. These are the three forces that are acting on this mass. Again, since this is a rotational motion, I am going to go to cylindrical polar coordinates, because this is rotating this way. I will use r and phi in this direction, and for this direction I will use z. So, let us see what happens to this mass. This is at a distance equal to radius of the cylinder from the center. It is being pulled down by weight mg. There is force n on it and there is frictional force F on it. Its acceleration in cylindrical coordinates is going to be r double dot minus r phi dot square r plus r phi double dot plus 2 r dot phi dot in phi direction plus z double dot z in z direction. However, in equilibrium, when it is moving stuck on the wall, r is constant and this is equal to r, and therefore r dot equals r double dot equals 0. Similarly, phi dot is fixed to be omega, and this implies phi double dot is also equal to 0, and it is not moving up and down, and therefore z double dot is also equal to 0. Therefore, the acceleration of the mass is given as A is equal to minus r phi dot square r. M A therefore is minus m r phi dot square r. How about the forces on the mass? There is a force in the negative radial direction n, there is mg and there is friction. So, this should be equal to n in negative r direction plus F minus mg in z direction. Equating the two sides, we get n is equal to m r phi dot square, which is nothing but m r omega square, and the other equation gives me F equals mg. Remember, F max is mu n, so that is going to be mu m r omega square. For the minimum omega, I should be applying the maximum possible frictional force for that omega, and therefore, for omega min, my condition becomes that mu r m omega square is equal to F equals mg. This m cancels and I get omega minimum to be square root of g over mu r, and that is your answer. So, what we have seen in this lecture is how frictional force acts on two bodies when they slide or tend to slide over each other, and how we use this in solving problems. In the next lecture, we are going to look at another form of frictional force which arises when bodies move through fluids, and that is the viscous or drag force.